Alright, so this video is going to talk about Graham's law, specifically diffusion and effusion of gases. Diffusion is just the mixing, and you can look at the rate of diffusion by basically looking at how fast it takes for the gases to mix, while effusion is when a gas moves through like a pinhole out into an open room. So effusion is what Graham's law focuses on, and it looks at the rate it takes for that gas to effuse, for it to get through that hole over a period of time. And it tells us basically that it's inversely proportional to the molar masses of those gases if we take the square root of them. And so that's going to be similar to their velocities, but it would be the rate is basically proportional to their velocities. It's inversely proportional, or an inverse square proportional to the molar masses, but it is directly proportional to their velocities. If they're moving at a faster rate, or a faster speed, they're going to be able to effuse more rapidly. If you happen to have equal amounts of the gases, because rate is the amount that it's moving over time, then basically the times in the molar masses would be directly proportional after you account for that square root function. So a couple of problems I'm going to have you do. The rate of effusion of a particular gas was measured and found to be 24 mils per minute, so it's a volume amount that's changing per time. And then under the same conditions, we see that pure methane gas effuses at 47.8 milliliters per minute. And so we want to find out how much what is the molar mass of that unknown gas. So if we take Graham's law, we have rates and we have molar masses. We want to find the molar mass of one of the two gases, and since molar mass is set up for gas 2 over gas 1, I would make my unknown gas gas 2 to make it a little easier to solve for x, and therefore the methane gas would be gas 1. So when I plug in my rates, it'd be the 47.8 over the 24.0, and then when I take the square root of the molar masses, it would be x over the molar mass of methane, which would be 16.05. The milliliters per minute cancel out, and now we would need to get rid of that square root sign, and the opposite of a square root would be a squared, so you need to square both sides of your expression, and when you do that and multiply by 16.05, you get that the molar mass is roughly 64. So we see that the rate was roughly the rate of methane was roughly twice the rate of the unknown gas. And because of that square root function, that basically means the molar mass of the second gas was about 4 times larger than methane. The other example I'm going to have you look at is involving argon and nitrogen. It took 12 minutes for 1 liter of argon to effuse through a porous barrier. Now I'm going to ask how long it'll take nitrogen to effuse under identical conditions. And so remember, I told you that time, if you have the same amount of argon and nitrogen, you don't have to do the rates. You can just look at the times and compare them to their molar masses of those gases. We're wanting to find the time for nitrogen, but we can find the molar masses of both nitrogen and argon by looking at our periodic table. You could have flipped it and had the argon be gas 1 and nitrogen being gas 2. Whatever you do, just make sure you're consistent with your molar masses. So since 12 minutes went with argon, and that's being gas 2, then the molar mass of argon needs to be in the numerator underneath the square root sign, and the molar mass of nitrogen, 28.02, needs to be under the the denominator of the square root sign. So if I take the square root of those values and I isolate x, in order to get x, you're going to need to take the reciprocal of both sides. You will get that it should take roughly 10 minutes. So nitrogen's smaller, so it's going to require less time for it to diffuse for that common amount, the common volume of the two gases. Remember on your homework that I did tell you in class that you could choose to do 3 or 4. You have to do all of the problems, but 3 or 4, you can choose one of those to do. You don't have to do the other. And that number 1 needs to have a decimal place after the quantity that's described there.